Okay, so first we're going to assign which one's an acid and which one's a base, and I also already gave the, I also already drew out the lone pairs of electrons. So sulfur, because it has a negative charge, has 3 sets of lone pairs of electrons, so 6 electrons total. And nitrogen, which has a neutral charge, because it's bonded to 2 hydrogens and a carbon, has 1 set of electron pairs. Okay, so this one with the sulfur is going to be a base, and the one with the nitrogen is going to be an acid. And why that is because sulfur has a negative charge, so it can accept hydrogen ions. And this acid, because if we look at the nitrogen, there are 2 hydrogen bonds. So there's two different hydrogens attached to this nitrogen, so it can give off hydrogen ions, so a proton. Next, we're going to draw the curved arrows. So if we look at, I'm just going to do a close-up of this one. Let's see. Okay, so this nitrogen, the reactant with the nitrogen and the fluorine, it looks like this. So the curved arrows are going to be from the bond between the nitrogen and the hydrogen to the nitrogen, and this one with the chlorine and the sulfur, let's see, has a curved arrow that's going from one of the electron pair sets to the hydrogen that just gave up its both of its electrons. Yeah. So, and it's the sigma bond that's transferred to the nitrogen that's giving off both electrons. So that's the curved arrow set. So then we're going to look at what the products are of this reaction. I'm sorry about this, but well. So there's the curved arrows. Like one of the curved arrows goes from one of the sets of electrons to the hydrogen, and one of the other curved arrows goes from the sigma bond to the nitrogen. And what the products are going to look like are, you're going to have the sulfur now has a neutral charge because it usually has 2 bonds and 2 sets of electron pairs. So you have this sulfur connected to the hydrogen, so this is pulled off, and this product with the fluorine and the nitrogen has now a negative charge, as this sigma bond just gave the nitrogen an electron pair. So you have the original electron pair, you have the new electron pair from the old hydrogen that just left, and you have the 1 bond to a hydrogen. So therefore that has a negative charge now. And so we said that this was our base, this was our acid. So this one is going to be our conjugate acid, because it's whatever's opposite to the base. So if this is a base, this is a conjugate acid. And because this one's an acid, this one is a conjugate base. So now that we've said that, we're going to decide which ones are weak bases, which ones are strong bases, which ones are weak acids, and which ones are strong acids. So the base is a weak base, and I can't spell weak. Weak base. This one's a weak acid. This is a strong acid. And this is a strong base. And I'll describe the whys of these in a second, but why this one's a strong acid and why this one's a strong base. But it's going to be more important to describe these, because when you have a weak base, its product is a strong acid. So its product, if whatever's weak, the opposite is going to be strong for its product. If that makes sense. So why this is a weak base is this reactant is more stable than this reactant over here. Why? Because it has a larger atomic radius because this sulfur has a negative charge, which means that the negative charge can be better distributed throughout the area because the space of the electrons, like the domain that it can be in, is bigger. Why this is a weak acid is because the electronegativity compared to this sulfur is smaller, because because the atomic radius is smaller, so the nitrogen is not as willing to give up a hydrogen. And then, so this, normally, when you don't have a negative charge, sulfur has a smaller atomic radius than nitrogen does. And in this case, because this nitrogen has a negative charge, so negative charge means bigger, more space for the electrons to move because it's a larger atomic radius. So normal sulfur doesn't want to give up the electrons as much as nitrogen, negatively charged nitrogen does. So it makes a strong acid because it's holding on to those hydrogens. And nitrogen really wants to bond to the proton in this case because this is a negative charge. So, yes. Next, so for the, let's see, pKa. So, which acid would you expect to have a higher pKa value? So, the inverse to acidity is the pKa. So, the more acidic you get, more acidic means lower pKa. So, higher pKa means low acidity. And out of these two, you have a weak acid and you have a strong acid. And the weak acid, because it's inverse to acidity, has the highest pKa. This one has the lower pKa, because high acidity means, well, inverse to it, low pKa. Low acidity means higher pKa. So the reactant with the fluorine and the neutral nitrogen has the highest pKa. And so to predict equilibrium position, equilibrium is going to, the position is going to move, it's going to be to the left. So equilibrium to the left, meaning that there's going to be like more starting materials present at 1 molar concentration at standard temperature pressure at the beginning of the reaction than the end, because these two products, or no, those aren't products. These two reactants are more stable than their products. So the species that are more stable are going to be present more often, because more stability means that they're more likely to be present. So which two species will be present in high concentration of equilibrium? Well, in high concentration at equilibrium, it's going to be these two reactants, because equilibrium is moving to the left, meaning this is going to be created more because they're more stable products, or more stable reactants. So, yes.